Hello, today this video is dedicated to Webwork problem. So for load shear bending diagram, LSB for Webworks. And that's homework 13, problem 1. Okay. All right. So we were given this beam, and they give us the dimensions and all the forces. And the first thing we need to find out is our reaction support, which is right here. I think that's an easy problem for us to solve at this point, right? What I would do actually for this video is I'm actually using my numbers and to solve this problem. Let's see. So the force here, mine is 18 kilonewton and W is 3 kilonewton per meter. And my A is 4.3 and B is 2.5 and C 8.3 and D is 2.4. And A is a pin support, E is a roller support, so that will giving us A and E. That will be our reaction support. What I'm going to do is I'm actually going to go to my Webworks, and I'm going to get the answer for this first step. So those are going to be my answers. So 22,896.86 and 2000314. Okay. So once I get that, I'm going to go back to my OneNote, and that's my answer for RA. It's 22,896.86 Newton and 20003.14 Newton. Okay. So that's not my focus of this video. My focus of video is to help you figure out how to fill in those blanks in these tables, right? We learned about the graphical approach for the load shear bending diagram. So we're about to draw this for load shear bending. And the first here will be our loading. And since we already calculate your RA, it is this value. Be 22,896.86 Newton. Then we will have this concentrated load right here. That's our F. That's 18 kilonewton. Then follow after, we have distributed load given the intensity as 3 kilonewton per meter. At E, we have this, I'm going to change to kilonewton, so it's 20.003. I'm ignore the remaining digits, but you know, for Webworks, you probably cannot. So what I'm going to do, I'm actually going to erase this one and change that to kilonewton as well. That will give me 22.897 kilonewton. All right, so that's our loading. And now we're moving up to our shear. So using our graphical approach, this force reaction is concentrated load, so it's going up. So we're going to jump up on the shear. So we're going to jump up to this value, which is 22.897 kilonewton. Then you move along the beam going this direction. there's no other forces, so it's going to be straight horizontal line until you are at this point. You drop down 18. So you have 22.897 drop 18. That will give up around here. So that's about 4.897, right? That's minus 18. Then you continue go, move forward. There's nothing going on here. So that will be straight horizontal line until we have encountered this distributed load. For distributed load, how do we use distributed load into shear? Remember, we have this, we're talking about shear is basically integral of our distributed load. In other words, the area underneath this distributed load is what we are going to integrate. So this is a rectangle. So the area here giving us 3 kilonewton. And what is my length here? So I'm going to go back to the geometry. Figure out mine is 8.3. That's my C. So times 8.3. And this area will be negative because this force is going downward, which is quite common, right? We don't normally see any load that's pulling the beam up. Often it's going downward. So that gives us negative 24.9. The unit will be kilonewton. So we're going to translate this number into our shear. How do we translate? We start at 4.897, right? This horizontal line. We're going to integrate a negative number until when we integrate to this point right here, we're going to minus 24.9. So have your calculator ready. So I have 4.897 minus 24.9. That will give me 20. So negative, so we'll be around here. Negative 20.003. Again, I'm going to show up how do we get this number. We start from 4.897. We're going to minus this area, your integrate. That will give us that value. Okay. And how do we connect those two dots? Remember, this is a horizontal line, which means a constant. When you integrate a constant, right? Your integrated constant, that gives you a straight line. That's power of 1. So that would be that. Okay. Then, however, I'm going to use this example to introduce a new concept. Is this intercept right here? That's what I'm curious. I want to know at what location this shear is going to be equal to 0. Right? And that is something new we have not talking about. And this is required for solving this problem. So now let's dedicate some time onto this one then. First question I want to ask you, since this is a linear line, and what will be the slope for this? In other words, what's going to be the slope for this line? Okay. Well, we learned the slope basically is derivative, right? If we have this shear is integral of omega, this shear is the area underneath the intensity. Another expression using derivative will be this omega is basically your dV over dx. That's your slope. So slope of the shear is going to be equals omega. That's what you just come up with. So going back to this, slope of the shear is going to be equal to your omega. That will be your 3 kilonewton meter. Okay. Now, knowing that slope, that will come up to help us finding about the location of this point, intercept. How do we do so? Now let's think about it. I'm just going to focus on this triangle here only. Okay. So the slope is 3 for that line here. If the slope is 3, Slope is rise over run, right? What's your rise? This is our rise. How tall is that? That's going to be your 4.897. That's how tall this is. Over run, it's this part, right? So it's that. It's this length. Okay, however, we can solve that. So this one will be equal to 4.897 divided by 3. That will give us about 1.632. Okay. So if you know that length is 1.632, did you figure out the location of this point? Yeah, we do, right? Because going back to the geometry here, this is 4.3, this is 2.5. So 4.3 here, and 2.5 here, and here is 1.632. So you know this location, okay? That's how we calculated the location here. So move on. Going back to our shear diagram. So after you integrate this entire area underneath this curve, you got to negative 20.6003. Then what do? We move forward. There's nothing going on, so it's going to be constant line until at the last point, this is jump upward 20.003. And so going back to 0. Fantastic. You got back to 0. Okay. That's what you wanted. You want everything get back to 0. If not, you're going to go back to check your step in the middle, see where could be the glitch. So that's a shear. Okay. Now I'm going to go back to the last here, which is our bending. Okay. Bending. We're talking about bending is basically integral of your shear. Or in other words, the shear is basically the slope of the bending. So we're using a graphic approach to figure it out for this problem. All right, so first thing you want to do, you're going to integrate this entire area above. What's this rectangle area? Right? So this rectangle area for mine would be 4.3 base times 4.897. So 4.3 times 4.897, that would give my value to be 21.057. So we start with 0. We're going to integrate this rectangle. So until we get into this last point, we're going to add 0.57. And since this is a straight horizontal line, it's going to become a linear parallel one. Okay. Then, to continue to move on, we're going to integrate this another area, which is right this rectangle. So what's this rectangle area will be? Okay, so what for this rectangle area, we're calculating our area will be 2.5, and what is our height will be 4.897. Oh, by the way, I think I made a mistake going back to this one here. This area, this is not 4.897. 4.897 is here. So I should times what? 22.897. Okay. So doing that, so I'm going to recalculate 4.3 times 22.897. That will give me 98.457. So knowing that, we're going to erase this. I'm going to change that to 98.457. Okay. So now we're going to integrate to this area. So we are using 2.5 times 4.897. That gives me 12.243, about there. So what does that mean? I'm going to add this value onto it. So here's my calculation. We're going to start at 98.457. We're going to integrate this blue area. We're going to add 12.243. 98.457. That gives me, excuse me, 110.7. Okay, so that's going to be the next line. That's going to be my 110.7 at this point. And it will be less slope, right? Because why? The slope of the bending is equal to what? Slope of the bending is equal to a shear. So the slope of this part is going to be equal to this value, which is 22.897. And the slope of the second segment will be equal to this part. That's our 4.897. So they are less steep. And if we just calculate this point, is going to be 110.7. Okay. Now, what we're going to do is we're going to integrate this area, right? We're going to integrate this area, and this is a triangle. So what is this triangle area? So this triangle area will be equal to half base. What's our base? This base is what you calculated, 1.632, right? From here. And the height is 4.897. So let's go ahead and put it into calculator. For 1.632 times 4.897 divided by 2, that gives me value 3.996. Okay. So in other words, I'm going to start at 110.7, this value, and I'm going to add, since I'm integrate, right? And they're all above x-axis, so I'm going to continue add. This value going to go up, plus 110.7. That gives me answer of 114.696. So that's going to be my next value. So it's going to be somewhere here. Okay. And that value is going to be 114. I'm going to erase this. This is getting in our way. Okay, that's better. So 11.7. All right, so this value is going to give us 114.696. Now, thinking about how do we connect those two dots? So far, all those first two segments, they're all straight line because those are horizontal constant. When you integrate constant, you get first power, linear line. However, what's this line we'll integrate? It's not horizontal line, it's a power of 1. And so in that case, you're going to get power 2, correct? And you're going to get power 2. And for this one, you are going to get this type of curve going up. Why is that? We have seen from a previous example in the video, because the slope of the bending is equal to shear. What's the slope of the bending if it's power going this way? That's going to be 0. And that's correct because the slope of this bending is equal to shear. Shear at this point is what? 0. And the slope at this point is going to be equal to this value, which is 4.897. Make sense? Okay, so you got that. Then we're going to continue to integrate. We're going to integrate our this triangle here. And be aware, this triangle is what? Below the x-axis, so you will get a negative value. So let's try to integrate this area. So this area is going to be equal to half base. What's our base? We're going to go back to our geometry to figure out. That is, oh, how do we figure out this? Okay, so this entire thing is 8.3 for this distributed load. And you figure out this length is 1.632. So what will be the remaining length here? Okay, that would be your 8.3 minus 1.632. 8.3 minus 1.632, that would give us a 6.668. So that's the length of there. So that's 6.668. Okay, then how tall is this? What's the height here? That would be this value, correct? 20.003. 20.003. That's the height of this rectangle. So we're going to calculate the area. So base times height times 6.663. That will give us, let me write down this here, dimension. All right, then times 20.003 divided by 2. That gave me 6.69. Okay, so would this area be negative? Yes, indeed, because it's below. So what happens is you reach 114.697 at this point when shear equal to 0. Remember, when shear is equal to 0, which means the slope of the bending is equal to 0, and we learned in calculus, if that's getting to slope equal to 0, you get maximum or minimum. So likely this is going to go down now. Why? Because you start to integrate this negative area. So start somewhere. Start on this peak, 114.696. You are going to integrate a negative number. You're going to minus this number, 6.69. And we got 48.006. So you start at this peak and you're going to get into this point about 48.006. All right, how do we connect these two dots? Again, this is what? A power of 1. When you integrate power of 1, we got power of 2, so you get a parabola. And the parabola likely is going to go this way. Why? Because we're using this. Slope of the bending here is equal to shear, is equal to 0. Only when you curve this way, you get that to be 0. And here, the slope of the bending here will be equal to the shear, which is negative 20.003. Everything lined up right. So very last thing we needed to do is to integrate the last rectangle, which is here, right? All right, so we're going to come down over here. Go ahead and integrate this last area. And this area, what's our base? What's the dimension here? What's our length? Go back, D. D is 2.4. So it's 2.4. And what's the dimension here on this length? It's going to be 20.003. 20.003. And so when we calculate that, we got 48.007. Okay? And again, this is negative because it's below x-axis. So we start at where? 48.007, and we are going to start at this value. That's where we end, right this point, right? Then we're going to integrate this negative area. That will give us 0, right? I mean, there's some rounding, we have it down, but you know you get it right. It's going to be 0. So you got back to 0. Fantastic, because that's where you want to get. You want to get back to 0. How do we connect those two dots? That's right, because this is what? Horizontal line. When you integrate a constant, you get a linear power of 1, so it's going to be a straight line. That's our bending diagram. To make this bending diagram look better, it's basically go straight, another straight line, and then parabola back, then we have a straight line. So that's our shape for this entire bending. Okay, so this is a complicated problem. How do we go back to answer the questions, fill the blank here? Once you get all those information, how does Webworks know your graphic is right? So that's another quick scale we're gonna just trying to cope with. So how do we do it? So x left and x right, and they have how many? They have 5 intervals. They have 1, 2, 3, 4, 5. How do they break it down to 5 interval? Right, here we go. So you see this one? This is gonna be our first interval. Okay, that's our first one. This is going to be our second. This will be our third. This will be our fourth and fifth. That's how they break out down. That's why it's important for us earlier to go ahead and find this point, this intercept, right here when you did that. Okay? So in that case, I will demonstrate, for example, for my first interval, x left to right, that my first one will be 0. That's my x equal to 0. And where's my ending point? 4.3. For my second interval, right here, then I will start at what? 4.3. That's my x equal to 4.3. And then I'll end here. That will be what? 4.3 plus 2.5, correct? So this one, 4.3 plus 2.5, that gives me 6.8. That's this point where you start, 6.8. Then we're going to add how much? Yes, this value, 1.632. That's going to be my 8.432. So that's my coordinate x value for that intercept point. Then we start at 8.432 for segment 4. And how much do we add? We add this value, 6.68. That will give me 15.1. Okay. And then this will be from 15.1 for my last segment 5. And it ends to, how long is this? Let's go back. It's plus 2.4. That's going to be 17.5. I mean, this value should be the entire length of your beam, right? You add all A, B, C, D. If we want to try to calculate that entire length, will be A plus B plus C plus D. So quickly add them together, just to trying to verify. Yeah, when I add them together, I indeed get to 17.5, which is the same value here. Okay, so that's the first two columns. How do we divide into 5 different sections. Now let's look at what's V left. V left means at interval 1 right here, what is my value when x equal to 0? What's my V value? V value will be this, will be 22.897. Now V right, what does that mean? At the segment 1, when it's right point, the end point, what's my V value? Since it's a horizontal line, that is also 22.897. That's how Webworks figure out if your graphic is right. And what's this function type? And this is going to be, if you click on that, you likely, let's see if I can get back to that. You're going to call it a linear, okay? So this is going to be, click on that, it's a linear. And a curvature, I mean, does linear have a curvature? No, it's going to be no curvature. And now M left. M left, which means at this point, x equal to 0, what is our M? So we're going to go down to the bending diagram to find our bending moment M. What's my bending? 0. And at this point, x equal to 4.3, what's my bending? 98.47. And what's the function type? Is this line a linear, right? A straight line. Okay. And the curvature, so since it's a linear, there should be no curvature for that one. That's how we solve this problem. So I will leave the rest for you to figure out for each following 2, 3, 4, 5 those segments. And have fun working, use your numbers. I know this is some problem that requires some time and effort. And have fun exploring. And I'll see you next time. Bye.